Hi, hello, this is Srija from CSDC section department. I am here to speak about the keeping time with Maxwell's equation. Maxwell's equations. Maxwell's equations are a set of four equations that describe the behavior of electric and magnetic fields and how they relate to each other. Now, Maxwell's first equation. Over a closed surface, the product of the electric flux, density, vector and surface integral is equal to the charge enclosed ds minus is equals to q enclosed. It is the equation 1. Any closed system will have multiple surfaces but a single volume. Why it is called Maxwell equation? That's after James Clerk Maxwell. He was a 19th century scientist who sort of put them together even though many others contributed. What is the name of Maxwell's theory? In 1865, Maxwell published a dynamical theory of the electromagnetic field in which he showed that light was an electromagnetic phenomenon. What are the four Maxwell relations? The Maxwell relations consist of the various characteristic functions. These functions are enthalpy H, Helmholtz free energy F, internal energy U, and Gibbs free energy G. Why is Maxwell theory important? James Clerk Maxwell is most famous for his theory of electromagnetism, which showed that light was electromagnetic radiation. His theory is considered to have paved the way for both quantum mechanics and Einstein's theory of special relativity. Why there are only four Maxwell equations? Maxwell's equations are composed of four equations with each one describes one phenomenon respectively. Maxwell did not invent all these equations, but rather he combined the four equations made by Gauss, also Coulomb, Faraday, and Ampere. Maxwell equation. Maxwell equation. Maxwell was the first person to calculate the speed of propagation of electromagnetic waves, which was the same as the speed of light, and came to the conclusion that electromotive waves are, and visible light are similar. These are the set of partial differential equations that form the foundation of classical electrodynamics, electric circuits, and classical optics, along with Lorentz force law. These fields highlight modern communication and electrical technologies. Maxwell's equations integral form explain how the electric charges and electric currents produce magnetic and electric fields. The equations describe how the electric field can create a magnetic field and vice versa. Here we have a equation integral C E bar dot dl bar is equals to minus d by dt integral S b bar into n cap into ds. What is mean by integral C? This is a line integral, and the meaning of E bar is induced electric field vector, and the dot represents dot product is equals to the component of E bar in the dl bar direction is equals to E into dl into cos theta. and then dl bar belongs to an infinitely small length of the closed path. Minus d by dt gives to the rate of change with time, and integral s b bar into n cap ds, the net magnetic flux through any surface bounded by the closed path C. And here integral on a closed path. Before going to the applications, we see first of all Maxwell's first equation. Maxwell's first equation is based on the Gauss law of electrostatic, which states that when a closed surface integral of electric flux density is always equal to charge enclosed over that surface. Mathematically, Gauss law can be expressed as over a closed surface, the product of the electric flux density vector and surface integral is equal to the charge enclosed. D bar into ds bar is equals to q enclosed. Any closed system will have multiple surfaces but a single volume. Thus, the above surface integral can be converted into a volume integral by taking the divergence of the same vector. Thus, mathematically, it is d bar into ds bar is equals to integral into d bar dv bar. It's a equation 2. Thus, combining first and second equations, we get d bar dv bar is equals to q enclosed. It is a third equation. Charges in a closed surface will be distributed over its volume. Thus, the volume charge density can be defined as PV is equals to dq by dv, measured using C by meter cube. On rearranging, we get dq is equals to PV dv. On integrating the above equation, we get q is equals to PV dv. It is a fourth equation. The charge enclosed within a closed surface is given by volume charge density over that volume. Substituting 4 in 3, we get dv ddv is equals to PV dv. Cancelling the volume integral on both the sides, we arrive at Maxwell's first equation, that is ddv is equals to PV. Now, Maxwell's second equation. Maxwell's second equation is based on Gauss law on magnetostatics. Gauss law on magnetostatics states that closed surface integral of magnetic flux density is always equal to total scalar magnetic flux enclosed within that surface of any shape or size lying in any medium. Mathematically, it is expressed as b bar into ds is equals to phi enclosed. It is a equation 1. Now, the difference between scalar electric flux and scalar magnetic flux. Scalar electric flux, they are the imaginary lines of force radiating in an outward direction. A charge can be source or sink. Scalar magnetic flux, they are the circular magnetic field generated around a current carrying conductor, no source or sink. Hence, we can conclude that magnetic flux cannot be enclosed within a closed surface of any shape. Now, let us see a Maxwell third equation. Time varying magnetic field will always produce an electric field. Maxwell's third equation is derived from Faraday's law of electromagnetic induction. It states that whenever there are n turns of conducting coil in a closed path, placed in a time varying magnetic field, an alternating electromotive force gets induced in each coil. Lenz's law gives this, which states an induced electromotive force always opposes the time varying magnetic flux. When two coils with n number of turns, a primary coil and a secondary coil, the primary coil is connected to an alternating current source and the secondary coil is connected in a closed loop and is placed at a small distance from the primary coil. When an AC current passes through the primary coil, an alternating electromotive force gets induced in the secondary coil. Mathematically, it is expressed as alternating EMF is equals to minus n d phi by dt. It is the equation 1, where n is the number of turns in a coil, phi is the scalar magnetic flux. The negative sign indicates that the induced EMF always opposes the time varying magnetic flux. If we take the if we take n is equals to 1, EMF alt is equals to minus d phi by dt. It is the equation 2. Here the scalar magnetic flux can be replaced by phi is equals to integral b bar dot ds bar. It is equation 3. Substitute equation 3 into alternating EMF is equals to minus d by dt integral b bar dot ds bar, which is a partial differential equation. Hence, we can conclude that the time varying magnetic field will always produce an electric field. Extended Maxwell's third equation of Maxwell's third equation for the static magnetic field, which states that the static electric field vector is an irrotational vector. Static field implies the time varying magnetic field is 0. And the last is Maxwell's fourth equation. It is based on Ampere's circuit law. To understand Maxwell's fourth equation, it is crucial to understand Ampere's circuit law. Consider a wire of a current carrying conductor with a current I. Since there is an electric field, there has to be a magnetic field vector. Consider a wire of a current carrying conductor with the current I. Since there is an electric field, there has to be a magnetic field vector around it. Ampere's circuit law states that the closed line integral of magnetic field vector is always equal to the total amount of scalar electric field enclosed within the path of any shape, which means the current flowing along the wire is equal to the magnetic field vector. Now we have some applications of Maxwell equations. The main application of Maxwell equations are we can calculate static electric field in a vacuum. We can calculate static magnetic field in a vacuum. It gives us the idea about electric circuits. What are the symbols in Maxwell's equations? E is equals to electric field, rho is charge density, I is electric current, B is equals to magnetic field, epsilon naught is permittivity, J is equals to current density, D is equals to electric displacement, mu naught is equals to permeability, C is equals to speed of light, H is equals to magnetic field strength, M is equals to magnetization, P is equals to polarization. What are Maxwell relations used for? The Maxwell relations are extraordinarily useful in deriving the dependence of thermodynamic variables on the state variables of P, T, and V. P belongs to pressure, T belongs to temperature, and V belongs to voltage. How do you derive Maxwell equations? Maxwell's equation illustrated the speed of electromagnetic waves is the same as the speed of light. This is used in understanding the principle of antennas. The flow of electric current produces a magnetic field. The four Maxwell equations can be expressed as div d is equals to rho, div b is equals to 0, curl is equals to minus db by dt, curl h is equals to d capital D by dt plus j. Why Maxwell equations are linear? The linearity of Maxwell's equations accounts for the well known fact that the electric fields generated by point charges as well as the magnetic fields generated by line currents are superposable is clearly is clearly a statement of the conservation of electric charge. With this, I will end this session. Thank you.